If math has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping. Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is Graphing Rational Functions Part 5. That's right, we're going to be graphing rational functions using transformations. So I saved the best and brightest technique for last, and here we are today. But first, please go ahead and subscribe to our YouTube channel, Fort Bend Tutoring. Go ahead and click on that bell icon so that you can be notified when we are uploading new and fresh content for you and your math classes. And let's go ahead and move on. Ladies and gentlemen, we have a snapshot of the 4 problems that we'll be doing in today's tutorial. And we have problem number 1, number 2, number 3, and number 4 ready to go for your viewing pleasure, so you know what to expect from FBT today. And continuing on, we want to remind you about rational functions. This is when you have a function in the form of p of x divided by q of x, where p and q are polynomials, and q of x cannot equal to 0 because we can't have 0 in the denominator of a fraction, because that will make it undefined. So within this video, we'll be covering graphing rational functions. However, we'll already assume by now you know how to find the domain, the range, the end behavior, as well as your intercepts, as we have showcased those steps in our previous 4 videos in this series. So we're going to be putting most of our attention for part 5 on graphing the rational function using transformations of common functions. So let's get into it. Here we have our parent function, f of x equals 1 over x, and many of the problems that you'll be viewing today will be in this form. So we'll be graphing rational functions together that are in a common form. We're calling this form right here the common form for most rational functions that you'll find in your classes. Continuing on, we have our transformations page. And on this page, I'm going to be showing you guys how to translate each and every one of your rational function problems that are in a common form into this expanded form here. The reason why you would want to write it that way is because we will be able to better define the types of transformations that are occurring in our rational function. For instance, your function may have a vertical stretch or shrink. It could have a horizontal stretch or shrink. It could have a horizontal shift, a vertical shift, and it could also have reflections across the x or y axis. And these values that you'll find in our expanded form, the a, the b, the c, and the d values, will tell you exactly what to expect from your graph of your rational function. Yeah, it's pretty cool. Also, if you want to check out more transformations in functions, check out our video that covers transformations in functions. I'll go ahead and put a link right here. Okay, so there you go. Check out that FBT video and you will be informed on that math concept. And finally, guys, we have problem number 1. We have f of x equals 2 divided by x plus 1. And the first thing we'll want to do is to rewrite our function in expanded form. So that means I'll be rewriting this function as f of x equals 2 times 1 divided by x plus 1. So this is going to be the expanded form of our original function, showcasing that our value of a, for instance, is 2. Yeah, our value of a is 2. And also, if you want to go ahead and dial things down, your value of b is 1. Matter of fact, let's go ahead and write those things out. My value of a is 2. My value of b is 1. My value of c is -1 because it's going to be the opposite of this value. Recall that our denominator here could be expressed in the form of b times x minus c. It is this c value that we'll need to find the opposite of in order to find out what that value is. So that's why I'm finding the opposite of 1 to get -1 for my c value. Then our d value is 0. So that's just letting me know that I don't have any vertical shifts in this function. So we won't be translating our graph up or down. It's going to stay where the parent function is as far as its height and horizontal asymptote is concerned. So most importantly now, we'll be able to write a mapping rule that we can use to transform our original parent function into the rational function that was given to us in problem number 1. So we can say that as far as our x values are concerned, we will be subtracting 1 for every x based on our c value, which coincides with the horizontal shift. So based on our c value in our rational function, now, we'll be able to take our parent function and subtract 1 for every x in that original xy chart. So the information that our c value is giving us is that it's letting us know that based on our parent function, we'll be subtracting 1 for each of the x values in that original xy chart. As far as our y value is concerned, the a value is going to inform us what to do with the y value. And we'll need to multiply each and every one of those y values by 2 based on that a value. That's going to be a vertical stretch, and it's going to stretch out our graph and multiply each and every one of our y values in our ordered pairs by 2. So we'll rewrite this as 2y as far as our mapping rule is concerned. So basically what this tells us is that for every x, go ahead and subtract 1 from x. And for every y, multiply that value of y by 2, and that'll transform your parent function into the current function that you're dealing with. Red boxing it. We'll go ahead and red box our map as well as the expanded form of our function. There we go. So now we get to actually apply the mapping rule. And starting out with the XY chart from our original parent function, so this shows all of our original ordered pairs from our original parent function. What we'll do is we'll take each x value and subtract 1 from it. So this -2 is now going to be -3. This -1 will be -2. This -1/2 will be -1 1/2. And I'm going to write it as a mixed number because for me, it's easier to graph a mixed number than it is an improper fraction. So here we have 0 minus 1, that'll give us -1. Now we'll have 1/2 minus 1, which gives us -1/2. We also have 1 minus 1, which is 0, and 2 minus 1, which is 1. So we're creating new ordered pairs for our current rational function based off of the ordered pairs that we had in our parent function and applying the mapping rule. We'll do the same now for the y values. So we originally started out with -1/2, and now multiplying that by 2, you'll have -1. Next, -1 times 2 is -2, and 2 times -2 gives us -4. We'll now look at the fact that at 0, it was originally undefined, and when you multiply something that's undefined times 2, it's still undefined. So we'll just use the null set here. Then 2 times 2 is 4. Then we'll have 1 times 2, which is going to be 2. And finally, 2 times 1/2 is 1. And there we have it. All right. So this is going to be our new XY chart for our rational function. Let's check it out. So one thing I do still like to do is I still like to start by graphing my horizontal and my vertical asymptotes, all right? And the horizontal asymptote for this particular function, based on the expanded form here, the degree of the numerator is 1 less than the degree of the denominator, so that tells me that the horizontal asymptote is y equals 0. So still using those rules for finding horizontal asymptotes in rational functions, and yes, here's the video right here. Go ahead and check out that link for horizontal asymptotes and rational functions. As far as our vertical asymptote is concerned, you would simply set the denominator equal to 0 and solve for it. So x plus 1 equals 0. When you solve for x, you'll end up with x equals -1. So this is going to be our vertical asymptote for our function. Knowing this information, I'm going to graph our two asymptotes first. So we'll start out with a horizontal asymptote of y equals 0. Well, that's practically the x-axis, right? So there we go with that. And then our vertical asymptote is going to be x equals -1, that vertical line going through -1. There we have it. Trying to make it as straight as possible, guys. There you go. So this is our framework. From here, we're plotting points. So our first point is going to be at -3, -1. So -3 and -1 gives us a point right here. We have -2, -2. That's going to give us a point right here. So next we have -3/2 or -1.5 and -4. So that's going to take us right here. Now we know that at -1, the function is undefined, aka our vertical asymptote. And so we move on to -1/2, 4. So at -1/2, I'm going to be at +4. That gives me a point right here. And next I'll be at 0, 2. That'll be our y-intercept if you needed to keep up with that. And then we'll have 1, 1 as our last point from the XY chart. Well, being as though we are dealing with common functions and this function is a transformation of our parent function, we definitely know that this graph is going to look like this right here, guys. Oh yeah. Putting arrows on the tips. There you go. Yeah. just like that. And since we already have everything fleshed out, we can go ahead and throw in our domain and range, okay? So for instance, our domain is going to be from negative infinity to -1 union -1 to positive infinity. All right. As far as our range is concerned, our range is going to be from negative infinity to 0 union 0 to positive infinity. And as far as end behavior is concerned, as x approaches negative infinity, y approaches 0. And as x approaches positive infinity, y approaches 0. So I'm going ahead and giving you everything anyway. There you go. And you even have your y-intercept right here. And in this problem, you won't have an x-intercept. So looks like I ended up giving you all your information anyway, right? Based on that, guys, let's red box it. We had our horizontal asymptote, which is y equals 0, vertical asymptote of x equals -1. We have a domain of negative infinity to -1 union -1 to positive infinity. We have a range, which is negative infinity to 0, 0 to positive infinity, and we have our end behavior here. Our end behavior is as x approaches negative infinity, y approaches 0, and as x approaches positive infinity, y approaches 0. Done and done, ladies and gentlemen. That was problem number 1. And here, I would like to remind you guys that you can actually set up a paid online tutorial today with Fort Bend Tutoring. And if you wish, you can actually set up a private tutorial with me. That's right, Mr. Whitt, me and you doing some math together. How about that? All right. So I just want to remind you guys of one of the services that Fort Bend Tutoring provides, and that is paid online tutorials. All right. Moving on to problem number 2. In problem number 2, we have f of x equals x plus 2 divided by x minus 1. So I especially am excited to show you guys how you can rewrite this in expanded form. For starters, we're going to be paying attention to the denominator, and we want to write the numerator in terms of the denominator. Let me show you what I mean. So we already know that f of x obviously equals to x plus 2 divided by x minus 1, right? Well, what I want to do is I want to rewrite the numerator in terms of x minus 1. So notice how I've already written the denominator in the numerator. However, we are well aware that our original numerator is x plus 2, right? So since we already have an x, we want to add to this value of -1 so that the end result is positive 2. So what will we need to add? We'll probably need to add 3 because we know that 3 minus 1 equals 2. So I'm rewriting the numerator and expressing this numerator in terms of the denominator. Once again, the denominator is x minus 1, which is why I already started with x minus 1 in the numerator, and then I had to add an additional 3 to that in order for it to equal to our original numerator. So now we have a numerator that is rewritten as 3 plus the quantity of x minus 1 divided by x minus 1. From here, we'll start expanding this. So we'll rewrite this as 3 over the denominator of x minus 1 plus x minus 1 divided by x minus 1. From here, you'll get your final form of 3 times 1 divided by x minus 1 plus 1. And this is our expanded form of our original function. Notice from this expanded form that we can show that a equals to 3, that b is still equal to 1, and c in this case equals to positive 1, and d equals to 1. So this lets me know that I'll have a vertical stretch with a scale factor of 3. I also know that I have a horizontal shift 1 place to the right, and I know I have a vertical shift 1 place up based on those a, b, c, and d values from our expanded form. So the next thing to do is to write a map for my transformation. So I know as far as the x values are concerned, I'm going to be adding 1 to every x value from my original parent function. In addition to that, for every y value, I'll be multiplying that y value by 3 and then adding 1 to it. So our transformation map is going to be x plus 1, comma 3y plus 1. This tells us what to do to all the original x and y values from our parent function in order to get our new graph that we need. Red box it. Let's go ahead and red box our answer right here. Next, we'll be actually applying our mapping rule to our parent function's xy chart. So for all the x values, all we have to do is add 1, right? So -2 plus 1 gives us -1. -1 plus 1 is 0. -1/2 plus 1 is going to give us +1/2. Then we'll have 0 plus 1, which is 1. 1 half plus 1, I'll write it as 1 1/2 or 3 halves. We have 1 plus 1, which is 2, and then 2 plus 1 gives me a value of 3. As far as your new y values are concerned, we'll need to take the original y values from the parent function, multiply those values by 3, and then add 1 to them. So negative 1 half times 3 is negative 3 halves, and then negative 3 halves plus 1 gives us negative 1 half. All right, then negative 1 times 3 is negative 3. Negative 3 plus 1 gives you a value of negative 2. Then multiplying negative 2 times 3, that gives you negative 6. Negative 6 plus 1 is negative 5. So then, because this value was originally undefined, it will remain undefined. And now we'll be multiplying 3 times 2 to get 6, and then 6 plus 1 is 7. Then multiplying 3 times 1, that gives us 3. And then 3 plus 1 is 4. From here, you'll have 3 times 1 half is 3 halves, and then 3 halves plus 1, it gives you 5 halves. And since I like mixed numbers, we know that 5 halves is equivalent to 2 1/2 as well. So there is your new XY chart. Let's go ahead and move on. So now we'll be going about graphing this. So your horizontal asymptote, even though you can derive this from the original function, if you use your expanded form, you'll note that every time you have it in expanded form, it'll start out with an initial horizontal asymptote of 0. However, your vertical shift will raise that horizontal asymptote up 1, so that your horizontal asymptote is y equals 1. Once again, if you use the original form of the rational function, you can easily find that y equals 1 is the horizontal asymptote. But when using your expanded form, the first term in the expanded form will always give you a horizontal asymptote of 0, and then you can use your vertical shift in addition to that to find out what the actual horizontal asymptote is. Here, since we have a vertical shift of 1, this 1 adds to our horizontal asymptote to give you y equals 1 as a horizontal asymptote. So with the vertical asymptote, you simply set the denominator equal to 0. So you'll end up with x equals 1. So now we have our horizontal asymptote and we have our vertical asymptote. And now let's graph it. So for the horizontal asymptote, you're going to be at y equals 1. So let's put a dashed line at y equals 1, just like that. Then for the vertical asymptote, you're going to be at x equals 1. There we have it here. Okay. From there, you can go ahead and plot your point. So we have a point at negative 1, negative 1 half, negative 1, and negative 1 half is going to give us a point here. Then we also have a point at 0, negative 2. That's also going to be our y-intercept. We also have a point at 1 half, negative 5. So at 1 half, we're going all the way down to negative 5 here. Then you'll have 1 1/2, 7. So 1 1/2, 7 is a point here. Okay. And then you have a point at 2, 4. 2, 4 gives us a point right here. And then you also have a point at 3 and 2 1/2. 3 and 2 1/2 gives us a point here. So based on that, guys, and our parent function, we should end up with a graph that looks like this. All right, looking good. Looking good. There we have it. All right. So that is going to be your transformed rational function for problem number 2. And let's give you the domain, the range, and the end behavior as well. Our domain, guys, is going to be negative infinity to positive 1, union 1 to positive infinity. All right. Then when it comes to your range is going to be from negative infinity to 1. Oh, that's an ugly infinity. Let's fix that. I hate that infinity. Oh my God. The infinities are ugly. There we go. That's a little better. Negative 1 to 1. Thank you. Really? Seriously. Let's fix this. Union 1 to positive infinity. And there is our range. Yeah. There we go. And then for your end behavior, let's call it EB. As x approaches negative infinity, y approaches 1. And then as x approaches positive infinity, y approaches 1. So this is your end behavior. Also, if you're curious about the x-intercept, all you'll need to do is set your original numerator of x plus 2 equal to 0 and solve for x. So that gives you an x-intercept of negative 2, 0. Negative 2, 0 is your x-intercept in case you needed that value as well. All right, well, let's red box everything. Red box in the horizontal asymptote, the vertical asymptote, the domain, also the range, and the end behavior, just like so. And that concludes problem number 2. With problem number 3, we have f of x equals x plus 1 divided by x minus 3. So we'll start by expanding our original function f of x, and we want to keep in mind that we'll be rewriting the numerator in terms of the denominator. So I have my x minus 3 here waiting on me, and since comparing the two numerators here, we had originally x plus 1, and now we have x minus 3 in the numerator. Using this as a base, we're going to need to add 4 to this value in the numerator in order to end up with an equivalent numerator. So I have 4 plus this quantity of x minus 3. This is going to be how I rewrite the original numerator in terms of the denominator. So now let's go ahead and start expanding this, and we'll have 4 over x minus 3 plus x minus 3 divided by x minus 3. Simplifying this and writing it in our expanded form, I'll have 4 times 1 divided by x minus 3 plus 1. And this is our expanded form of the original rational function for problem number 3. Red boxed it. Yeah, I sure did. When it comes to our transformation map, we're going to be able to write this and show that all we need to do to our x values is add 3. Okay, remember this value in that x minus 3 form, our c value is the opposite of that negative 3 there. So because of that, we'll have x plus 3. We'll need to add 3 to all of the original x values in our parent function. All right. Then as far as the y values are concerned, you'll need to multiply that y value by 4 based on our vertical stretch here, and then add 1 to that product based on the vertical shift of 1. All right, so this is going to be our map for problem number 3. Let's see about applying it after I red box it. Just like that, guys. Red boxing it. You know how we do up in here at FBT. Don't act all brand new. You know what this is. All right, let's apply the mapping rule. So notice that we have our mapping rule of x plus 3, comma 4y plus 1. We'll apply that to the xy chart of our parent function that I showed you at the beginning of the video. So we're going to be adding 3 to all of the x values. So negative 2 plus 3 gives me positive 1. Negative 1 plus 3 gives me positive 2. Negative 1/2 plus 3 gives me 2.5. And I'll write it like this. Then 0 plus 3 gives me 3. And then 1/2 plus 3 gives me 3.5. And 1 plus 3 is always 4, of course, and then 2 plus 3 gives me 5. All right, so those are our new x values for our ordered pairs that we'll use to graph our function for problem number 3. Then I'll need to multiply each y value in the original parent function by 4 and then add 1 to the result. So 4 times negative 1/2 gives me negative 2, and negative 2 plus 1 is negative 1. Then negative 1 times 4 is negative 4, negative 4 plus 1 is negative 3. Then multiplying 4 times negative 2, that gives us negative 8. Negative 8 plus 1 gives us negative 7. Then, since our y value for this point was originally undefined, it will remain undefined. Then we'll multiply 4 times 2 to get 8. 8 plus 1 is 9. Multiplying 1 times 4 gives us 4 plus 1, that's 5. And now we have 4 times 1/2, that gives us 2. 2 plus 1 is 3. And this is going to be our new XY chart for our function here. Let's go ahead and see about graphing it. For starters, we're going to always go back to the horizontal asymptote. So once again, I told you that since this is going to always be in horizontal asymptote of 0, we'll add 1 to that to get y equals 1 for our horizontal asymptote there. For the vertical asymptote, you set the denominator equal to 0 and you'll get x equals 3. All right, so using this information, let's go ahead and graph the horizontal asymptote first at y equals 1. Just like so. All right, and then we'll graph our vertical asymptote at x equals 3. So that'll be a vertical line going through the dashed line going through x equals 3, just like that. All right, go ahead and fill that in a little bit. There we go. And now we'll plot our points. We'll start off with 1, -1, which is going to be at 1, -1 is here. Then we'll have a point at 2, -3. 2, -3 is here. And then we have a point at 2.5 and -7. So 2.5 and -7, yes. Then we'll have a point at 3.5 and 9. So 3.5, 9 is a point here. We'll have a point at 4, 5. 4 and 5 is a point right here. And then we also have a point at 5, 3. So 5 and 3 is here. Now, let's go ahead and graph this. Based on the parent function and our transformations, you're going to have a graph that looks like this. There you go. Look at you making your graph look nice. Oh yeah, there you go. Put arrows on both ends. That's right. So this is our graph for problem number 3, guys. Not bad, huh? Look how fast that is. It's not bad at all. Not bad at all. Your domain for this function is going to be from negative infinity to 3 union 3 to positive infinity. The range for this function is going to be from negative infinity to 1 union 1 to positive infinity. Your end behavior is going to be as x approaches negative infinity, y approaches 1. And then you'll have as x approaches positive infinity, y approaches 1. And there you go for your end behavior, guys. As far as your x and y-intercepts are concerned, you can set the numerator of the original function equal to 0 to solve for your x-intercept, which is going to be at -1, 0. All right, that'll be the x-intercept. And your y-intercept, you can just plug in zeros for all your x's and simplify this to find out that your y-intercept is at 0, -1/3. All right, so once again, the x-intercept, simply set the numerator equal to 0 of your original function. And for the y-intercept, simply replace all the x's with zeros and simplify to get y equals -1/3 for the y-intercept. All right, let's go ahead and red box this. Red box in the horizontal asymptote, the vertical asymptote, the domain. Oh, yes. And the range. And the end behavior is right here, guys. There you go. And that was problem number 3. There it is. All right, let's move on. For problem number 4, we have g of x equals -2x minus 5 divided by x plus 4. As far as expanding this problem is concerned, remember that we want to be able to rewrite the original numerator in terms of the denominator. And notice that our original numerator here has -2x. So because the denominator only has an x, I'm pretty sure that when we take that denominator of x plus 4, I'll need to multiply that by -2. And when we distribute that -2, what happens? You end up with -2x minus 8, right? But in our original numerator, you had -5. So that means to get that -8 that we now have to be a -5, you'll need to add 3. Yeah, you'll need to add 3. So I now have the new numerator written as 3 minus 2 times the quantity of x plus 4. Once again, rewriting the numerator in terms of the denominator. So now, as we expand the new numerator, we'll rewrite it as 3 divided by x plus 4. And this is going to be minus 2 times x plus 4 divided by x plus 4. All right, so there we go. From here, we'll say we have 3 times 1 divided by x plus 4 minus, as these x plus 4s will cancel out, 2. And this is going to be the expanded form for problem number 4. Red box it. Red boxing it, guys. Just like that. Next up, as far as creating our map, we're going to say that we'll need to subtract 4 from all of the original x values in our parent function based on the fact that our c value is -4 here. Then as far as utilizing that a value of 3 and the d value of -2, which affects the y values, by the way, you'll end up writing the y coordinate as 3 times y minus 2, and this completes our map for our transformation for problem number 4. Red box it. Red boxing it, guys. So let's go ahead and take our original XY chart from our parent function and use our map to create the XY chart for our new function here. So we'll need to subtract 4 for all of the x values in the original parent function. So -2 minus 4 gives us -6. -1 minus 4 gives us -5. -1/2 minus 4 gives you -4.5. And 0 minus 4 is -4. 1/2 minus 4 gives you -3.5. 1 minus 4 is -3, and 2 minus 4 gives us -2. Now for our y values, we'll need to multiply each of the y values by 3 based on that vertical stretch, and then subtract 2 from that product based on the vertical shift. So 3 times -1/2 is -3/2, and -3/2 minus 2 gives you -7/2. All right. So this is negative 7/2, aka negative 3.5. Then we'll have 3 times negative 1, which is negative 3. Negative 3 minus 2 is going to give us negative 5. Then multiplying 3 times negative 2, that gives you negative 6. And negative 6 minus 2 is negative 8. We know that in our respective point, the y value started out as being undefined, so it will remain undefined. And now we move on to 3 times 2, which is 6. And 6 minus 2 gives us 4. Multiplying 3 times 1, you'll have 3 minus 2 gives you 1. And now multiplying 3 times 1/2, that is 3/2 minus 2, which gives you negative 1/2. All right, so this is our new XY chart for our graph. As far as the horizontal asymptote is concerned, recall that this part of the expanded form starts out with a horizontal asymptote of 0, but then this vertical shift moves it down 2. So that means our horizontal asymptote is y equals negative 2. As far as the vertical asymptote is concerned, set the denominator equal to 0 and solve for it. So you'll get x equals negative 4 as your vertical asymptote. So I'm going to start graphing by graphing those two asymptotes. We have y equals negative 2, so this is going to give me a horizontal line through y equals negative 2. Then I'll graph my vertical asymptote at x equals to negative 4. So that's going to be right here. All right, just like that. And now we'll plot our points. Our first point is going to be at negative 6, negative 3.5. So negative 6, negative 3.5 is a point right here. Then we have a point at negative 5, negative 5, negative 5, negative 5 is here. And then we have a point at negative 4.5, negative 8. So negative 4.5, negative 8 is a point here. Next, we'll be looking at negative 3.5, 4. So negative 3.5, 4 gives us a point right here. We also have negative 3, 1. Negative 3, 1 gives us a point right here. And we also have a point at negative 2, negative 1/2. Negative 2, negative 1/2 is here. And so once again, based on our transformations and our parent function, we'll have a graph that looks like this. Arrows on both ends, guys. Arrows on both ends. In other words, get your arrows popping on your graph. Okay, so there is our graph, guys. Using our transformations, we were able to take our parent function and graph the function that they gave us, noticing how valuable that expanded form can be to us. Our domain, guys, is going to be from negative infinity to negative 4 union negative 4 to positive infinity. Okay, then you're going to have a range. Your range is going to be from negative infinity to negative 2 union negative 2 to positive infinity, like so. Then for your end behavior, EB, as x approaches negative infinity, y approaches negative 2. And as x approaches positive infinity, y approaches negative 2. All right, so that takes care of our end behavior. And as far as your x and y intercepts go, you can take the original numerator, which is negative 2x minus 5, and set it equal to 0 to find that your x-intercept is going to be at negative 5/2, 0. All right, let's go ahead and expand that. And then for your y-intercept, you're plugging in 0 for all the x's in the original function, and you'll find that your y-intercept is at 0, negative 5/2. As a reminder, you can check out our video on finding the domain and x-intercepts of rational functions, and I have a link for it right here, guys. Check that out for finding the intercepts of rational functions. Amen, amen. So let's go ahead and red box our work here. We have our horizontal asymptote. We got our vertical asymptote. We have our domain. Yes, we do. We have our range. Thank you. You have your end behavior. That's right. As well as your x and y intercepts right here to boot, ladies and gentlemen. So that concludes problem number 4 and this video for graphing rational functions using transformations, part 5 of our 5-part series. That's right, guys. We made it all the way through to the end. Thank you so much for watching this video and this series. And please feel free to share this series and this video with your classmates, your teachers, and your friends and family. We greatly appreciate it. I personally appreciate it. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Whitt, and Fort Bend Tutoring. Peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.